Hey, everybody. Thank you for attending my presentation today. I guess I could say this evening or today or tonight, and any of those would probably be applicable to somebody who's attending the presentation. This is my presentation, An End to Brainless LabVIEW Programming. If you have never met me before, my name is Darren Nattinger. I have worked at NI for almost 22 years now. The vast majority of that time, I was in LabVIEW R&D, implementing features that you may have heard of or used, like the VI Analyzer Toolkit and QuickDrop. And this year, I moved into the tech support department. So I'm working alongside some other senior people like Norm Kirchner and David Corney and others to build up the experience level of the tech support department at NI. So in this presentation, I am going to be talking about how we can end brainless LabVIEW programming. Now, before I start, this is the point where if we were in person, let's say we were at NI Week, I would have said, you know, if there's another presentation that you really want to see right now, why don't you go see that, and then you can watch the recording of this presentation later. But it's my understanding that there are not any other presentations going on right now. So instead, I'll say, if you would like to get an hour of sleep and watch this presentation later, you can do so because the slides and the video are linked at the link on the page, bit.ly/brainlesslabview. So without further ado, I believe that is all of the intro content I have. Let's go ahead and get started. So when I say brainless programming, what am I talking about? I'm not talking about being stupid. What I'm talking about is intelligent programmers who do things without even thinking about them. Now, there are certain things in life that we can do without thinking, and that's okay. Like tying our shoes or eating a bowl of cereal or taking a shower. We can do those things on autopilot, right? We don't have to engage our brains too much. It's just something that we do and then we get it done. But there are other things in life where you definitely should have your brain engaged while you're doing them. If you're doing your taxes, if you're driving a car, purchasing a home, these are all things that you really need your brain engaged in order to take care of that action without something bad happening as a result. So now if we take that brainless term and apply it to LabVIEW, there are reasons that we do things in LabVIEW without thinking. One of the most obvious is that things that we've just always done a certain way. We can just keep doing things that certain way because it's how we've always done it, right? We don't need to think about it. And a lot of the times that's related to best practices. When you first learn LabVIEW or when you work on a team that has style guidelines established, there's just the best practices that you follow. And so as you're programming, and you encounter one of those situations, you just say, oh, well, the best practice is to do this, so I'm going to go ahead and do it that way. But there's a problem to that. The problem is that if we do a lot of things in LabVIEW in a brainless way without thinking, a lot of times we end up writing inefficient code. Even worse, sometimes we end up writing incorrect code. It actually functions the wrong way. And sometimes some of these best practices end up causing us to have code that's difficult to read and difficult to debug. But one of the main reasons I hate brainless LabVIEW programming is because I'm the efficiency guy, right? I'm the guy who teaches you how to use QuickDrop so you can program efficiently. And I hate it when people waste time writing code that they don't even need just because they're following some best practice, something that they just do brainlessly. So in this presentation, what I need you to do is to keep an open mind. I will be covering 8 things that all LabVIEW programmers do without thinking. And I am going to make the case that those things are often the wrong thing to do. So this presentation may be a little bit, I guess, different from what you're used to seeing because I'm going to take a lot of conventional wisdom in LabVIEW and just tell you that it's just plain wrong. So please don't get offended, though. It's not like I'm telling you you're a bad LabVIEW programmer because most of the things in this presentation I also do. I have to retrain my brain to not do these things. So hopefully I have set things up in a way that makes, if you were about to fall asleep, maybe you have woken back up slightly now because I'm about to tell you all the wrong things that you're doing in LabVIEW. Are you ready? All right, let's go. Item number 1. All VIs need error case structures. So if you look at these diagrams on the screen here, these are very familiar patterns, right? You've got an error in and an error out. And so you wrap the code on this sub-VI's diagram with an error case, right? Why do we do that? Well, it's so that we can make sure that the sub-VI code doesn't execute if there's an incoming error. And this pattern is pretty normal. We see this in a lot of sub-VI templates. We see it in the class VI templates, the method VI templates, the accessor templates. And as far as I know, you can still get points taken off when you take the CLD exam if you don't wrap your sub-VI diagrams in error case structures. So, obviously all reasons why we should wrap our code in error case structures, right? Wrong. Hardly any VI that you write needs an error case structure on its block diagram. And there are several reasons for this. The first one, the LabVIEW compiler can optimize the generated code for your VI in a whole bunch of ways if there are no decision points on that block diagram. A decision point would be a case structure or a select function, something that picks out of multiple different options when the code executes. The more decision points you can remove from a diagram, the more optimized your generated code for your VI can become. And then stylistically, there's less diagram noise if you get rid of 99% of the error case structures that you have on your block diagrams. Your diagrams are going to become cleaner, and it's going to take you less time to construct them if you don't have to drop that anymore. Now, you're probably using templates for a lot of things, so the case structure is there. But when you create a new VI that needs an error case structure frame, that's one less thing that you'll need to spend time doing if you stop wrapping every sub-VI's diagram in an error case. Now, I mentioned before the class templates, like the method VI, the accessor VI, those templates already have an error case structure in them. Why is that there? Well, there are times that you do want an error case structure, and it's a lot easier to remove it if you don't need it than to add it if you do need it. And I've just got a tip on the slide there. Instead of right-clicking and doing remove structure on a case structure, you can select the structure and press Control-Space, Control-Shift-R. That does exactly the same thing. Might be a little faster for you to use the keyboard shortcut instead of the right-click menu. So a few other reasons why hardly any VIs need error case structures. Just about every error that gets generated on a block diagram comes from a built-in function, like a function or a property node or something like that. And just about all of those, if they have an incoming error, they don't do anything. So the built-in functions in LabVIEW are already behaving the way that we expect them to, where they just pass an error through and don't do anything. Let's just let them do all the work. Why should we add G code to do what they're already doing? And another thing, do you really care if your code runs faster because it skips execution in an error condition? If you've got an error condition, you probably care about more important things than how fast a sub-VI runs in an error condition, right? And then finally, remember I mentioned the compiler optimizations. So you can optimize your block diagrams execution for when the code has an error or when the code has no error. Errors are hopefully the thing that you expect the least. So we should probably optimize our block diagrams for the non-error case, right? And the optimization for the non-error case is to not have an error case structure at all. Now, notice that the title of this slide is hardly any VIs need error case structures. There are definitely times where you do need an error case structure. The most common reason would be if your block diagram is manipulating the error stream in some way. So you can see the picture on the left there. We're doing a specific clear errors on the error coming out of a sub-VI. And we don't want this code to mess with upstream errors that have been passed into the sub-VI. This is a good example of a time where it makes sense to wrap your code in an error case structure. Now you can see two different sort of styles that I've used over the years for documenting code when an error case structure is necessary. The one on the left, you can see I'm attaching a comment to the incoming error wire. The one on the right, I'm using this green colored label. I've started doing the method on the right more just because it's easier to discern when you open up a block diagram and you see that green label on the error case structure. It's a lot more clear what's going on. You know, if you just need a quick visual cue that, oh, the person who wrote this diagram actually considered the error behavior of this block diagram, that green label communicates that a lot faster. I guess I'll check. Are there any questions before I move on?
There are two questions. One is Mark Blond is asking, optimize in speed or memory size?
The question was when I'm talking about the optimization, it's going to be the optimization of the generated code, which that's what I was told when I put this presentation together. My assumption was that implied execution speed.
Okay. And then Derek Bomarito is asking, wouldn't that be better to separate the error wire branches and merge them in? instead of using the case structure.
Oh, looking at the code on the left there that I have on the diagram,
Yes.
The question is why not just merge? You could certainly do that if you wanted to. Either approach is fine. All right, I am going to move on. All right, so the next brainless thing that we do is we wire every single error output terminal on our block diagrams. Now, why do we do this? Well, the most obvious reason is we want to make sure there aren't any errors that we aren't accounting for in our code, right? Another reason is the bottom two pictures there, where people want to prevent automatic error handling dialogues from popping up for errors they don't care about. So what they'll do is they'll dangle a clear errors function or clear errors VI, or just like an empty flat sequence structure off of the output of those functions. You do not need to wire every error output terminal on your block diagrams. Look at that first picture there. That is a format into string function with a string constant wired to the format specifier. And that string constant has the proper percent codes in it. If it didn't, this VI would be broken. So there is no way that format into string is going to error out. Now, I've been told that technically that's not true. You could conceivably get a error 2 memory is full out of that format into string. I would wager that if you do get error 2 memory is full, you've probably got bigger problems than the fact that you did not wire the error output of your format into string. So I will take the engineer's route and say that there is no practical time that that function will error out. So if you know that a function isn't going to reasonably error out, you don't need to wire its error output terminal. This gives you more opportunities for compiler optimizations, like I talked about, and for executing your code in parallel. If you were wiring the error output from that format into string, chances are you're serializing it with something else on the diagram that doesn't need to be serialized. Now the bottom picture there.
I have to relay the comment from Chris Stryker. Boo. Okay.
I'm sorry, you just got muted there. I didn't hear what you or Chris Stryker said, but it probably wasn't that consequential anyway. So the bottom picture there, if you know that a function might error out, but you don't actually care, then there is no need to wire its error output terminal. So you can see the code there is deleting a file, it is closing a reference. The author of this code has commented the code to say that, yeah, I'm trying to delete the file and close the reference, but I don't care if those things error out. Now, one argument I've heard against this pattern is that people will often wire the error output from those guys into a flat sequence structure, and then include a free label in the flat sequence structure that says, I don't care about the error output from this function. And the argument is that you're documenting your code better that way. And my counter argument is that if I did not wire the error output, that is my documentation to you that I don't care about the error output from that function. So this is the part of the presentation that Chris Stryker may have been booing. Automatic error handling is the worst feature that has ever been added to LabVIEW. I see code like the top picture there way too often. I think that looks silly. I think it's ridiculous that people are dangling things on their block diagram just to appease automatic error handling. You should be turning off automatic error handling instead. For the love of LabVIEW, turn off the setting and tools options that turns it on all new VIs. You can see in my screenshot there, that's what I've got the red arrow pointing to. There's the second checkbox right under that, enable automatic error handling dialogues. You can uncheck that if you want also, which means the dialogues will never pop up no matter what. I keep that option checked because that allows me to find out what code people have written and given to me that has auto error handling turned on so that I can then go yell at them to turn it off. This is another thing I should point out. It's something that I think we did better in LabVIEW NXG in that automatic error handling is a per project setting. So if you want automatic error handling turned on, you enable it for the entire project. If you want it turned off, you disable it for the entire project. Now it's not a per VI setting that you have to go micromanage like you do in LabVIEW. So I have written a VI analyzer test and posted it on ni.com. You can Google the term there to go download it. It will not only detect, but also turn off any VIs in your code base that have automatic error handling turned on. All right, I'm going to move on to my next item, which is how to quickly benchmark your code. So if you've got some code,
Darren, quick
Yes.
thing. Chris
Sure.
Stryker is saying, for those of us that aren't perfect, it is a nice uh-oh catcher.
I think I've run my point into the ground, so I will just keep moving on here. So quickly benchmark your code. So you've got some VIs that you want to see how fast they execute. And so what do? You wrap the code in a flat sequence structure, you drop a tick count before and after, and you do a subtract, and you're on your way. You know how long that code took to execute. Well, the problem is that a brainless benchmark often results in a brainless benchmark value. So the tick count function, stop using that. You need to use the high resolution relative seconds VI instead. It gives way better resolution than tick count does. Another issue I've seen, people will very often wire constants into their VIs that they're trying to benchmark. The problem is that the LabVIEW compiler is pretty smart, and so it's going to start trying to constant fold out code so that when you actually run your benchmark, a lot of what would normally be computed at runtime has been computed at compile time, which will screw up your benchmarks. Also, if you've got functions like built-in LabVIEW functions that are part of what you're benchmarking, if you don't wire some of the outputs, again, the LabVIEW compiler actually looks at what outputs you've wired from various functions, and if you don't wire them, their code will not be included in the compiled code. And so again, you're not going to get an accurate benchmark if in the real world you are wiring the outputs of those functions. You don't want to update any indicators on the front panel during your benchmark. That's going to slow things down. If debugging is enabled, that's also going to slow things down because the compiler includes debugging hooks in your generated code in case you decide to probe or turn on execution highlighting or pause or anything like that. And then if you've got code that happens to be executing in parallel to what you're trying to benchmark, that can skew the results. But wait, there's more. The VI that contains the code you're benchmarking, if the panel of that VI is open, your results can be skewed. So make sure you are basically calling a wrapper whose panel is not visible when you run your benchmarks. If there's any file I/O going on, any access to the LabVIEW memory manager going on, a lot of these other factors can skew the first iteration of your benchmark. So make sure you toss the first iteration when you're making calculations. You are probably doing your benchmarks on a single computer. There are a lot of factors that can make that machine an outlier. There are factors that could even make that particular run of LabVIEW an outlier. Do you have a performance grid of 40 machines that are identical that you can run your benchmarks on? LabVIEW R&D does. You probably don't. So watch out for those single computer benchmarks that could be off from whatever machine happens to be running the end user code. Basically, don't trust a single machine benchmark for any decision you make that's like an application critical decision. However, the rest of the rules that I just gave are pretty good to get good benchmark data most of the time. So if you look at the first screenshot here of the tick counts in the sub-VI and the constant wired in and the indicator being updated and all that stuff, compare that to what the code should look like, which is we have now taken the code we want to benchmark, we've put it in a harness, we're using high resolution relative seconds, we're, making sure that we're not running any other code in parallel. The front panel of the VI containing the code needing to be benchmarked is not open. We are taking all of our benchmarks and deleting the first one before taking an average. And all of these factors will probably give you a decent benchmark, although not one that you should make any critical decisions on unless you're running it on a more robust, benchmarking framework, like, with multiple machines or anything like that. So that's what I have to say about benchmarks. I know it's often a simple topic, wrapping the code and just doing the tick counts, but I've seen this posted on the NI forums quite a bit, actually, where somebody will say, hey, I benchmarked this thing, and why is it so slow? And some factor that I mentioned in this presentation, or maybe even other things that I didn't even think of, somebody points out and says, hey, your benchmark is total garbage because you didn't take this one thing into account. So put some more thought into that benchmarking harness. Fabiola, we got anything before I move on to the next part?
Nope.
All right, I'll keep going. My next one, avoid global variables. They're evil. You can abuse globals. You're going to have race conditions. Never use them. You got to use functional globals. They're the greatest, but whatever you do, don't use global variables, right? Wrong. Global variables are a tool that we have in this huge toolbox called LabVIEW. Global variables are very easy to use and easy to operate, but you do have the potential to use them in an unsafe manner that could cause accidents in your code. You know what? An automobile is very easy to use and to operate, but you have the potential to use an automobile in an unsafe manner that can cause accidents on the road. Does that mean that we never use automobiles? No, we still drive cars all the time. We just use our brains when we do so. Remember my second slide with my car, which had a little cat in its headlight, if you were paying attention? We use cars in a way where our brains are engaged. In just the same way, we can use global variables in a way where our brains are engaged. Use them in a safe way. Wear your seatbelt when you program with global variables. How do you wear your seatbelt? Well, the safest way to use a global is to write to it in one place or in 0 places. Those are your 2 safe choices when you're using a global. Now, some people who are so freaked out and frightened about globals, what they'll do is they will replace them with functional global sub-VIs that have a read operation and a write operation. You know what? That's exactly the same functionality as a global variable, but it took you longer to write that code, and you're still going to have the same race conditions. If you're really paranoid, but you still, have the need to use some sort of global data storage, there's a trick you can use where you take the global VI itself and you make it private in a library. Then you've got a read VI that's public and a write VI that's private. So only the library VIs, and hopefully only in one place, can write to the global, but anybody can read from the global. That's the trick where you privately scope the global in a library. So hopefully it's clear now, I actually do like global variables. I wrote a blog post about it a long time ago, back when I used to write blog posts. You can Google the term there and go read my post about why I like global variables. And I got to say, I got surprisingly positive feedback in the discussion thread for that blog post, a lot more positive than I thought it would be. Fabiola, is the chat exploding with global haters right now, or are we good to proceed?
Actually, no, there's absolutely true. Had a big discussion about this. What about global to store a DVR ref? And then that was Aaron Gelfman. John Lucanis is saying an automobile is easy to use, not according to my teenage daughters and the front bumper of my car.
Oh, no. Sorry to hear that, John.
And Tim Robinson is telling Aaron Gelfman that he does it all the time. So
cool.
There you go.
All right, I am going to move on now. So here in Austin, Texas, we have a tourist destination called Mount Bunnell. Now, Mount Bunnell is not a mountain because we do not have mountains in Austin, Texas. We have hills, but we have called this hill a mountain. And one of the great things about Mount Bunnell is that you can get to the top of it in about 5 minutes, which again is another reason it's not a mountain. And you can just see the most beautiful sunsets from the top of Mount Bunnell. You can look down and you can see the Colorado River. You can see all the pretty mansions that are along the edge of it. And you can just, off in the distance, you can see the sunset, and it's really beautiful. It is almost as beautiful as this block diagram that you see on the slides right now. Isn't that a beauty? Look how straight those wires are. Look at that train track pattern. That is the kind of block diagram that you open up and you just say, ah, how beautiful is that, right? Everybody's code, if they're writing their diagrams clean, looks like this, right? It should not look like this. I'm sorry. Here's the thing about train tracks and LabVIEW class programming. If you have a method VI in a class that does not manipulate the class data, do not make that a pass-through wire on the method VI. For one thing, it kills your possible parallel execution, which I already talked about before. In case you didn't know this, you can have a dynamic dispatch VI that only has a class input. It does not need to have a class output. It can, dynamic dispatch just fine just with the input. But here's the thing. I have spent so much time debugging class-based applications where there's hundreds of method VIs that take a class in and a class out. And somewhere down the way, I've got the code paused, and I've been probing those class wires, and all of a sudden, the class data, I can detect at this spot right here, something got messed up in the class data. So then I look upstream and I see dozens of sub-VIs that pass the class in and the class out. Now I have to go start digging into each of those sub-VIs, which have their own sub-VI hierarchies, trying to find the spot where the class data got messed with. And that is why I hate it when a method VI has a class output when it doesn't modify the class data. So I'm about to show you a block diagram that is not as beautiful as a Mount Bunnell sunset, but you just need to prepare yourselves, okay? I think we should start writing diagrams like the top picture and not the bottom picture. The bottom picture is a beautiful sunset. The top picture is, I don't know, the outside of a dirty landscaping company. I don't know, that just came up off the top of my head. But look at that. We've got 6 sub-VIs, and all of them probably have their own very deep sub-VI hierarchy, but only 2 of those 6 sub-VIs could potentially modify the class data. So instead of passing that class wire through the other 4 and all of their dozens or possibly hundreds of VIs in their hierarchies, now the class wire is only being passed through the VIs that can actually modify it. This is going to make this code less pretty, yes, but much easier to debug whenever something goes wrong with that class wire. That is 4 sub-VI hierarchies worth of class VIs that I don't need to dig into to try to find out how that class data got messed up. Now, Delacour has written a blog post on this topic. If you go Google Delacour just passing through, you'll find it, and it's talking about a lot of these same topics. Now, here's the thing. In this particular API, this is just an internal API that's part of LabVIEW App Builder, these sub-VIs have to run in serial. That's why the error wire is being passed through. We have to run those 6 sub-VIs one at a time. But if this were an API where serial execution was not required, if this were an API where parallel execution was just fine, then we could write the diagram like this. So now, since we've removed those class pass-through wires, and the classes only pass through a wire if they can modify the class, now we've got code that not only is easier to debug because now we don't have the pass-through wire on VIs that don't modify the class, but also we have code that's probably going to run a lot faster because this code can take advantage of parallel execution, whereas the previous code could not. So I'm suggesting writing code that looks like the top picture instead of the bottom picture. It's something we're not used to. It's something that doesn't look as nice, but in the long run, it's something that will execute faster and will be easier to debug. Surely somebody has something to say about this.
Yes, there were several. So Mark Valla is asking.
Give me 1 or 2.
Okay. So Mark Valla is asking, does this mean we shouldn't use class property nodes?
So that's a great question. The question is, what about class property nodes? So I got to tell you that my personal pattern is that on a block. So I guess I'll preface by saying, out of the thousands of class property nodes I have written in my LabVIEW career, I would probably say less than 10 of them do anything on their block diagrams other than bundle and unbundle. The vast majority of my class property nodes use bundle and unbundle. I like class property nodes because I like the syntax. It's clean, it's easy to read a block diagram, and you see the text names of the properties, and you can also stack them in parallel. I would say that most diagrams where I use a class property node, I do not wire the class output terminal on that property node because, again, I am just gaining access to the member data of that class. I'm not modifying anything, so I might as well just wire the class input, pull the data out of the property node that I need, and not wire the class output. So that's pretty consistent with the message that I'm giving here. What else?
Oh, that was Tom was asking. Tom McClellan is asking, what if you have a reference in and the method does something to what's being referenced? Maybe an object in a DDR. Okay, so in that case, I assume what we're referring to is a class that wraps only references because, Stephen has talked about this before. I agree with him. If you have a class that contains references, it should only contain references. If you have a class that contains by value stuff, it should only contain by value stuff. And the thing about references is that the actual value of the reference, unless it's some weird API, I guess, the value of the reference doesn't change. So in those cases, your class wire is acting like a reference wire. And as a result, when I use a reference-based API like VI Server or .NET or something like that, that
reference wire doesn't change throughout the whole code. So it's perfectly fine to do pass-throughs on that just for convenience, because you don't have to worry about something in or something about the reference itself changing. That's why classes as reference wires, I treat differently than classes as by value.
So Mark Long is saying the top one is actually more beautiful because it is more faithful to the truth. Jimmy Sang is asking, is there any memory or speed impact for branching the class wires?
So the question is, when you branch the class wires, you always hear horror stories of, I branched my waveform wire that has 1 billion elements in it, and LabVIEW crashed, right? So the LabVIEW compiler tries to be very, very smart about how it can operate on things in place. Hopefully most of you guys who are listening to this know what in placeness is. If not, it would be a whole presentation for me to discuss that. But the LabVIEW compiler does a pretty good job of figuring out, oh, you are only reading data from this wire. You are not manipulating the value in this wire. So I'm not going to make a memory copy. I'm going to access the original buffer that has that data in it. If you do modify the value in that wire, at that point, LabVIEW will sometimes have to make a copy. But to answer the question, in general, no. When you branch these class wires, and all the branches except one, in the case of this diagram here, are just reading data in the class, you don't have to worry about extra buffer allocations for those branches.
Okay, one last one here, and Everman is asking, how about when they just pass through the error wire? Which do you give preference to use for data flow?
Okay, so the question is, passing through the error wire, passing through the class wire, even though like computer science purists probably wouldn't like what I'm about to say, the error wire has pretty much become the canonical way that we force data flow in LabVIEW. There was a big argument within NI's walls back when we argued about adding error terminals to the wait primitive. It was the most highly voted idea on the LabVIEW ID exchange. People wanted an error in and an error out on the wait primitive because people needed to serialize it so often between one operation and another. And so it got 1,000 votes or something on the ID exchange. And I said, that's a great idea. We should add error terminals to it. And I and 1,000 other people, I guess, ultimately got shot down because there's, technically speaking, the wait function isn't going to do anything with the error value, right? It's not going to generate an error. They couldn't decide among themselves whether it should still wait if it had an error input. And there was all this ambiguity that they decided we're not going to add error terminals to the wait function. I disagree with that, because even for things that don't have anything to do with the error, if you want to serialize them on a block diagram, the most common way we all do that is on top of an error wire. So I would say the answer to the question is the error wire is almost always used as the thing to serialize a block diagram. There may be sub-VIs or functions that have something else on them, like a class in and a class out, or a reference in and a reference out. But just by common practice, we pretty much all use the error wire for serialization. All right, so I think I'm gonna keep moving on here with more brainless things to talk about. This is a fun one. We have to close all references, right? In LabVIEW, if you get a reference to something, you better close it when you're done. That is one of the most commonly accepted best practices in LabVIEW. It's the easiest way to avoid memory leaks. When in doubt, close that reference, right? Wrong. Now, there are some references that you do need to close. Let's make sure we know which ones those are. Anything having to do with ActiveX or .NET or hardware, definitely close those references when you're done. There's even additional things you have to worry about, like I know with ActiveX and .NET, you have to close them in a specific order from child to parent, right? Otherwise, you might screw something up. If you ever use like OpenVI reference, or you use a property known to gain a reference to an application or VI, definitely close those references once you're done. If you're doing any scripting and you are working with the project API, so you're opening references to the project or to items in the project to do any sort of scripting, definitely close those references. But there are a lot of references that you totally don't need to close. Don't worry about closing anything that inherits from the GObject class in VI Server. That's panel and everything that it owns. that's diagram and everything that it owns, that's connector pane. All of those things inherit from the GObject class. Check out that first picture. Isn't that ridiculous? If you get a panel reference from a VI and then you close that reference and then you use that panel reference you just closed, it works just fine. There's no error. That close reference function on that block diagram is completely useless and is just taking up space. If you have static control references, you do not need to close those. If you have a reference to this VI or this application, you do not need to close those. Look at that bottom picture. Maybe you didn't even know about this, but if you drop a property node and it references the application class or the VI class, and you don't wire the reference input, that is called an implicit property node, and it implicitly refers to the application that owns this VI or the VI that owns this property node. You don't need to close those references coming out of those guys anyway. So all of the things on this screen, you don't have to close those references. You're wasting your time and your block diagram space if you drop close reference functions on any of the references you see on this block diagram. Are there any questions on that before I move on?
Mr. Chris Stryker is saying, can we rely on Desktop Execution Trace Toolkit to tell us if we ignore important references?
That is a great question, Chris. I actually don't know how Desktop Execution Trace Toolkit handles these errors on this screen that are not being closed. That would be an excellent thing for us to find out. I don't know. If the Desktop Trace Toolkit did talk about these references, it probably shouldn't.
Yeah, John Locanis is saying sometimes it tends to not see all closes, so you never get it to 0 reference leak errors. Derek Pomarito is saying my user interface framework sped up to orders of magnitude by not closing VI references. Turns out the core loop is greedy, and LabVIEW will clean them up in a non-leaky way anyway.
That sounds great.
That's
all right.
it.
I'm going to move on. All right, so this block diagram construct is probably pretty familiar to a lot of us that have been programming in LabVIEW for a long time. You've got some nested code, right? Like if this condition, then check this. If this condition, check this. If this, like you basically have to nest a bunch of case structures, right? And once you finally get to the innermost condition, if all of those previous conditions have been met, then you're going to take some item and store it in an array, right? That's exactly what this diagram is doing. We have probably all written code that looks like this. We probably still write code that looks like this, but we don't need to write code that looks like this anymore because we have conditional tunnels on for loops. So check it out. Those shift registers disappeared. All of those pass-through wires on all of those case structures frames disappeared. Now only the diagram where we actually want to generate the item we care about is generating that. In this case, it's a cluster. And we're just passing that all the way out to the loop border and passing a true all the way out to the loop border to add it to the array. And every single other frame uses the default values so that the items are not added. It's kind of funny. After this feature came out, I was giving a presentation where I talked about this feature. Then later in the presentation, I did a live LabVIEW demo. And while I did that demo, I wrote the code the old way. I started adding a shift register with the pass-through wires. And then I think somebody in the audience pointed out, hey, why don't you use that conditional tunnel thing you just told us about? And so it's like, this is an example of one of those patterns that's hard to break if you've been doing it for many years. One other point is that conditional terminals, so this diagram is actually more efficient than the previous diagram because apparently there's some compiler magic that I don't fully understand that allows us to more efficiently build up that array on the for loop border than we do with the build array function inside the case structure. Any questions on that before I move on?
Oh, just Andres saying, so happy when it appeared on LabVIEW. I agree with that.
Oh, I was so excited when we got this feature. All right, so the next part. If any of you guys know me, you knew that this part was coming, all right? So something that I hear all the time is people telling me that they are used to programming with the palettes in LabVIEW. So I'm the quick drop guy. And when I see somebody using the palettes, I'm like, hey, you should use quick drop. I get all of these reasons why they still use the palettes. People tell me that they're already fast enough with the palettes. They don't need a faster programming approach. and that they have muscle memory for where everything is in the palette. So they don't even think about it. They just move their hand, the certain way to get the item out of the palette. And then I get resistance that somebody doesn't want to learn a new way to program in LabVIEW. So they don't use Quick Drop because, they already know how to use the palettes. I've actually had people tell me they don't know the names of the objects that they drop. They only know where they are in the palettes. I'm pretty sure that's a bold-faced lie. How can you not know what a for loop is called? And then, this one's my favorite. LabVIEW is a graphical programming language, man. I should use a graphical tool to create my VIs, not a text-based tool like Quick Drop. And then when Quick Drop first came out, which was, I guess, 12 years ago now, people said, I'd like to use it, but I have to go download the object shortcuts off ni.com, CS for case structure, AD1 for increment. That's kind of a pain to have to go download something every time I want to use. Blah, 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 blah. Stop using the palettes, okay? Those seconds that you use to go find an object in the palette, those add up. The average time to find an object to drop it from the palette, even an object exactly where you know where it is about 2 seconds, because you hover your mouse and you wait a couple hundred milliseconds before that palette comes up. Then you hover your mouse over the next sub palette, wait a few hundred milliseconds, and all that adds up to about 2 seconds for every object you want to drop. Well, with Quick Drop, especially when you're typing in object shortcuts, again, like CS for case structure, RN for property node, you can drop an object with Quick Drop extremely fast, 8 times faster than the palettes. Now, just to clarify here, I'm talking about the fastest possible way to drop something with Quick Drop, which is called Super Quick Drop. If you have LabVIEW open right now, you can try this. You press Control Space, Quick Drop comes up. Type in the object shortcut for something you want to drop, like ADD for add, for example. If you just click in the VI where you want to drop that object, it drops right there. You don't have to press Enter on your keyboard. You don't have to double click in Quick Drop. You just click in the VI once Quick Drop says the name of the thing you want, and it gets dropped right there. That is the fastest way to drop things with Quick Drop. It's called Super Quick Drop. It's the best way to use Quick Drop. So what I did was I timed myself. I'm still pretty fast with the palettes, even though I don't use them anymore. It took me about 18 seconds to make a random number strip chart, just programming as fast as I could. It took me less than 10 seconds to do the same thing, but with Quick Drop. And the time saving is largely because there's 4 objects you got to drop when you're writing the random number strip chart. And again, with the average time for using the palettes, if you average that out, it's about 8 seconds to drop those things. If you average out the time that it took to drop the objects with Quick Drop, it's only 1 second. So that's where you get your time savings, is by using Quick Drop. So here's the thing about Quick Drop object shortcuts. So these are essential for programming fast with Quick Drop. If you don't use object shortcuts, you are not using Quick Drop to your full potential. But the thing is that for a while, you had to go download shortcuts or make your own. But in LabVIEW 2016 and later, we've got a default set of object shortcuts installed. And here's the thing, there may be some people listening to this presentation that program on LabVIEW other than LabVIEW English. You might be using LabVIEW German or French or Chinese or Korean or Japanese. And the object shortcuts are the same across all of the languages. So case structure obviously is, different words in all languages, but it's still CS keys across all languages. So we have the object shortcuts optimized mostly for the left hand, assuming most people have their right hand on the mouse and left hand on the keyboard. And so no matter what language LabVIEW you're using, you're still going to use those optimized left hand object shortcuts most of the time. So if you have decided you want to use Quick Drop and you want to use these object shortcuts, I made a game and it's posted on ni.com. It's called Falling Shortcuts. And it's basically a game in LabVIEW that you can use to learn all of the object shortcuts that ship with LabVIEW. So I encourage you to download that game if you want to try and get better about using Quick Drop and not using the palettes anymore. Any questions about Quick Drop other than, the fact that it's definitely the best way to program in LabVIEW?
Sam had already put the link for the game. There's some discussion about the names are not always coming to mind if English is not your first language.
Right.
However, they did, that was Andre Berman, but he did make a point that you do remember the names of your own functions. So if you have the project open, Quick Drop will find those functions.
Right. That's true. So another thing I didn't talk about is the fact that you can use Quick Drop to not only drop objects that are typically found in the palettes, but also any VI that's in your project. You can also drop a Quick Drop. And I'll point out that you can customize these object shortcuts. So if you don't like the ones that I made, because I made all the ones that are with LabVIEW, if you don't like those, you can configure them, click the configure button in QuickDrop that you see on the screen there, and you can customize them to be whatever you want, anything that's more intuitive to you. Just keep in mind, if you start using somebody else's LabVIEW, the shortcuts will be different unless you move your LabVIEW INI file over. Anything else on that?
Okay. Yeah, Josh Bates is asking, QuickDrop in 2019 is much slower for me than 2017.
Okay, so QuickDrop, if it's slower, I can think of a few reasons for that. You may want to mass compile your resource dialog QuickDrop folder. If something happened where the compiled object cache got messed up, then built-in features in LabVIEW that are written with LabVIEW can become slower. That could be the case. If you have a project open and the project's like super huge, QuickDrop is going to be a little bit slower because it's going to be parsing the contents of that project to populate the list. Those are the couple things I can think of off the top of my head. We can, if you want to move on to the discussion in one of the forums on the GLA after this, we can maybe try to narrow it down if one of those two things doesn't end up being the cause of the issue. But those are the couple I can think of off the top of my head.
That's it.
All right, well, that is all the content I have. If there's any questions about any of the Brainless LabVIEW stuff I talked about in this presentation, let me know. You can definitely download the slides and link to the video recording there at bit.ly/BrainlessLabVIEW. Hopefully, some of the items in this presentation stuck with you. Hopefully, you weren't too offended. Hopefully, you can come away from this sort of giving a second thought maybe to some of the best practices that you follow in LabVIEW that may be actually hindering your programming, maybe making you less efficient or making your code less efficient. And hopefully, if you took away at least one or two nuggets from this presentation, then we're on our way to programming LabVIEW in a less brainless way.
And just for those of you that don't realize, this is a really big treat to have Darren presenting because he created QuickDrop. He also has worked on BI Analyzer. He's the scripting ninja. What other accolades do you have, Darren?
I am the 7-time undefeated, now retired, world's fastest LabVIEW programmer.
There you go. That was a mouthful. Any other questions? We have about 10 more minutes before I kick you out to go to the breakout rooms.
And yeah, I'll go over.
John Locanis is saying that you're always thought-provoking.
Thanks, John. I'll head over to the breakout room for the main stage after this, just in case anybody wants to discuss any of this stuff further.
Yeah. So Ernesto Garcia Ruiz, and you know he lives in Japan, he's saying no brainless LabVIEW should be equal to mindful LabVIEW. So I guess if you want to be more zen about it, you could call it mindful LabVIEW. You
can call it whatever you want, Ernesto.
Oli Magno is saying, thanks so much. Your presentations are very, very valuable. So thank you so much, Darren. And thank you so much for presenting late for Austin time. So our friends, the other side of the world could enjoy your presentation live.
I'm happy to do it, y'all.
Thank you so much.
Sure.